Hey there, it's Shannon Math-Chick-Myers, and today we're checking out section 8.2.3 from the ZIL Intro to Differential Equations text. This one covers complex eigenvalues and deals with finding general solutions of homogeneous systems of linear equations. So let's do this thing. If lambda 1 is equal to alpha plus beta I, and lambda 2 is equal to alpha minus beta I, where beta is positive, non-zero, and I squared is equal to, of course, -1, are complex eigenvalues of the coefficient matrix A. Just to clarify here, the capital letters that we use are matrices. So we've got column matrices we're dealing with and coefficient matrix. The eigenvalues will also be complex, of course, but there's a way that we can make them real, and we did this back in chapter 4. So here's our first theorem. 8.2.2 of this subsection. Let A be the coefficient matrix having real entries of the homogeneous system capital X prime is equal to capital A times capital X. And let capital K1 be an eigenvector corresponding to the complex eigenvalue lambda 1, which was equal to alpha plus beta I, where alpha and beta are real. Then K1, where K1 is an eigenvector corresponding to lambda 1, e to the lambda 1 t, and K1 bar, it's called, times e to the lambda 1 bar t, are solutions of capital X prime equal to A times X. It is fairly easy to rewrite a complex solution in terms of real functions. As in chapter 4, we used Eulers' formula. So we're going to check this out just a little bit. Let capital K1 be an eigenvector of the coefficient matrix A, which has real entries, corresponding to the complex eigenvalue lambda 1 equals alpha plus beta I. Then the solution vectors from Theorem 8.2.2 that we just went over can be written as capital K1 e to the lambda 1t is equal to capital K1 e. Now we're going to split this in terms of alpha t, okay, times e to the I beta t. And this is all from Euler's formula, which we looked at length in chapter 4. So you can always go back. I made a playlist for the differential equations videos. And this, in turn, is going to equal to capital K1 e to the alpha t times the quantity cosine beta t plus I sine beta t. And then our capital K1 bar, all right, e to the lambda 1 bar t will be equal to capital K1 bar times e to the alpha t, and then again times e to the, this time it'll be negative I beta t, which will give us, I'll move my equal sign over a little bit and I'll put a line here, k1 bar e to the alpha t times the quantity cosine beta t minus I sine beta t. By the superposition principle that we checked out in section 8.1 from Theorem 8.1.2, the following vectors are also solutions. So vector x1 equal to 1/2 times what we started with up above, so vector k1 e to the lambda 1 t plus vector k1 bar e to the lambda 1 bar t. But if you substitute in what we got, as the final result for those, I've got one of them underlined already. Here's the other one. That's going to be equivalent to 1/2 times, we'll factor out the k1 and k bar 1 vectors. We'll have an e to the alpha t cosine beta t, and then we'll have minus 1/2 I, or I over 2, times vector k1, and that one will be negative, okay? Plus k bar 1. And then, of course, we'll have e to the alpha t times sine at beta t. And then x2, the second solution vector, will be 1/2 times negative k1 e to the lambda 1 t plus vector k bar 1 e to the lambda bar 1 t, which will equal to, so with a little bit of factoring, we'll have I over 2, so this is an I, times the quantity negative k1 plus k bar 1 e to the alpha t times cosine beta t plus 1/2 times k1 plus k bar 1 times e to the alpha t sine beta t. And again, this all came from Eulers formula, so that we can, soon make these real, the coefficients real. All right, so both 1/2 times z plus some z bar and 1/2 I times negative z plus z bar are real numbers for any complex number z equal to ai, a plus I, b. Therefore, the entries in the column vectors one half times vector k1 plus k bar 1 and 1/2 I times the vectors negative k1 plus k bar 1 are real numbers. By defining vector b1 as 1/2 times vector k1 plus vector k bar 1, and vector b2 by I over 2 times negative k1 plus k bar 1, we have the following theorem. So this is 8.2.3, real solutions corresponding to a complex eigenvalue. Let lambda 1 equal to alpha plus I beta be a complex eigenvalue of the coefficient matrix A in the homogeneous system x prime equal to A times x, and let column vectors beta 1 and beta 2 denote the column vectors defined above. Then vector x1 will equal to vector b1 times cosine beta t minus vector b2 times sine beta t, all of that times e to the alpha t, and x2 is going to be equal to vector b2 times cosine beta t plus vector b1 times sine beta t times e to the alpha t. These vectors are linearly independent solutions of x prime equal to A times x on the real number line, which means, of course, they'll form a fundamental set of solutions. So note, the matrices B1 and B2 are often denoted by B1 equals capital R-E K1, so that's for the real part, and B2 equals to capital I and then M for imaginary K1. Since these vectors are respectively the real and imaginary parts of the eigenvector K1. Okay, so here we go. Let's look at an example. We want to find the general solution of the given system. So remember, you have to put all the pieces together. I like to identify what my A is. So A is equal to the coefficient matrix. 4, 5 is the first row. Negative 2, 6 is the second row. And then our vector for our variables is just going to be x and y, since that's what we have in the system. And then A minus lambda I is equal to 4 minus lambda, 5, negative 2, and 6 minus lambda. Groovy? So the first step, as always, is to what? Beautiful. Find the eigenvalues. And remember, to find the eigenvalues, we need to solve the determinant of A minus lambda I equal to 0. All right, so let's do it. Our determinant will look like this. It's a 2 by 2, so we just cross multiply. So we multiply that main diagonal and then subtract the other diagonal product. And so we'll get 4 minus lambda times 6 minus lambda. And then minus a negative 10 is plus 10. Continuing, we'll have 24 minus 6 lambda minus 4 lambda is minus 10 lambda. And then we'll have plus lambda squared plus 10 is equal to 0. Rewriting and combining the constants, we'll have lambda squared minus 10 lambda plus 34 is equal to 0. And then that's not going to factor, so lambda is equal to the opposite of b is 10 plus or minus the square root. This is just our quadratic formula of b squared minus 4 times a, which is 1, times c, which is 34, all over 2 times a. So lambda will equal to 10 plus or minus the square root of, we'll have 100 minus 136 when we work that out, which will give us negative 36 in the underneath that square root over 2. And then we will have lambda equals 10 plus or minus 6i over 2. So then we'll have lambda is equal to 5 plus or minus 3i. So lambda 1 will be 5 plus 3i, and lambda 2 will be equal to 5 minus 3i. Groovy? All right, so the next step, so we do this one a little differently, remember, because so for this step, we really just need to find the vector k1, and then we get our whole solution. So let's do this. We're using lambda 1 only, and that lambda 1, our alpha was equal to, let's see, 5, and our beta was equal to 3. So we have 5 plus 3i. So alpha equals 5, and beta, that more beta-like, equals 3. So remember, what we need to do is we need to find a minus lambda, which is 5 plus 3i, right, times the identity, I2, and then times k, and that's equal to the 0 vector. So we solve this equation. So when I plug in 5 plus 3i for lambda here and here, what will happen is I'll get this matrix. So 4 minus lambda is 4 minus 5 plus 3i. We'll have 5 and then negative 2, and then we'll have 6 minus lambda, which was 5 plus 3i. The k vector is just k1, k2, and then we have our 0 vector for this dimension is 0, 0. So this is going to give us 4 minus 5 is negative 1, minus 3i, 5, negative 2, positive 1 minus 3i, times k1, k2 equals 0, 0. And now we'll go ahead and just solve that system. Not so bad. We'll have negative 1 minus 3i times k1 plus 5 times k2 has to equal to 0. And then negative 2 times k1 plus 1 minus 3I times k2 has to equal to 0. Groovy? Continuing, if I solve for k1 in terms of k2 in that second equation, that looks good. So from this second equation, right, we'll have negative 2 k1 would be negative 1 minus 3I times k2, which will give us k1 is equal to 1 minus 3I times k2 all over 2. And then now we just need to let k2 equal something that, whatever we want, all right? So if we let k2 equal, let's let it equal to 2 because then the 2's will divide out. Then k1 is going to equal to what? Beautiful. 1 minus 3I. Groovy? So now let's see how we can write that. So our k1 vector is going to equal to k1, which is 1 minus 3I, and k2, which we set equal to 2, which, if we write it as the real plus the imaginary part, will be 1, 2, plus I times negative 3, and then 0. And then the vector b1, remember, is the real part of vector k1, which will be 1, 2. Vector b2 is that imaginary portion of, and that one, we don't have to include the I, we're going to include just the real part. So we'll have negative 3, 0. Isn't that amazing? All right, so let's now take a look at our general solution. All right, so our general solution will be so we're going to be using the x1 and the x2 from that theorem. I just copied and pasted it here. And so what we'll have is this. Our general solution x is going to be equal to c1 times vector x1 plus c2 times vector x2, right? Just as a solution, or just as a reminder, alpha was equal to 5 and beta was equal to 3. So here we go. X equals to C1 times X1. So our B1 is the real portion, right? So that was 1, 2, and then we're going to need to group this, times cosine beta is 3, so 3t, minus b2, which was negative 3, 0, times sine at beta, which was 3 times t. So b2 is from over here, is here, and then our b1 was there. And alpha, all of the alphas here, I'll do in yellow. And the betas, I'll do in green. Okay. I think I got all my colors going on. All right. All right. So the first one's done, right? All of that was our x1. Now our x2, oh, sorry, and we have this multiplied to e to the alpha t. Alpha was 5. And then plus our second one. So we'll have C2 times B2, which is our -30, times cosine beta t, so cosine 3t, plus B1, which was 1, 2, times sine at 3t, and all of that is going to be multiplied to e to the alpha t, so e to the 5t. So corresponding all of our little numbers here. We have it, and that's it. That's all she wrote. So this is our complete solution, and just so you can see, x1 is all of this, and our x2 is all of this. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hit that subscribe button for my channel and like the video. Have a wonderful day. Bye.